All right, let's quickly look at g. G is one of your parent functions, right? Or it should be, cube root of x, also known as x to the 1/3. That's the one where you're on some kind of red flag alert to start with, right? What was it? Cusp alert, right? Fractional exponent less than 1 and greater than 0. And so at the root, at x equals 0, you're going to have a critical value at x equals 0. And it's going to be either this, that, or that, vertical tangent. And of course, if you know what the graph of the cube root of x looks like, you can answer this question real easily. That's the inverse of x cubed. It comes in like that, goes vertical, and then comes out. So you could do the first derivative test at x equals 0 and realize that it's going to be a positive slope to the left and right. So there is no local max or min, but is it an inflection value? X equals 0 is going to show up as a possible inflection value and a critical value. Does the concavity change there? Yeah, it's concave up to the left and concave down to the right. So yes, if you did the second derivative chart, you would see that f double prime changes from positive to negative. So this one is interesting because x equals 0 shows up as both a critical value and a possible inflection value. And in this case, it can't be both. So it's not a local max or min, but it does end up being an inflection point. So I'm not going to do the derivative stuff on that. Now, for piecewise functions, they're always the exception to the rule. So you're not going to approach these the same way. What you're going to want to do is just analyze what the graph looks like, and even better, if you can sketch the graph, you'll be able to answer some questions about it pretty quickly. So for a piecewise function, remember, you look to see where it switches. It switches at 0. So we really want to know what's the limit from the left and the limit from the right. So coming in from the left of 0 and at 0, it's the top piece. The square root of negative x is your graph of square root of x, and what does the negative in front of an x do to any function? Good, that's a y-axis reflection. So it's going to be 0 at 0. That would be the limit from the left. You can use direct substitution for that, and it looks like that. And then, of course, x squared, we know what that looks like. It's going to be an open circle at 0, but really it's filled in because they're sharing it, and then x squared looks like this. So there's the graph. Does this function have any critical values? Are there any places in the domain where the derivative is 0 or undefined? Where the slopes are 0 or undefined? Yeah, at x equals 0. And notice we didn't do that from any kind of calculation. We're just doing it from analysis. Is that going to be a local max or min? Yeah, it's a local min. Now this is it ends up being a continuous function. So you could say, since this function is continuous at x equals 0, and y prime of 0 is d and e, since y prime changes from negative to positive at x equals 0, y has a local min there. Cool. Are there any PIVs? Yes. Where is the PIV? And also at x equals 0. And we know that because if the first derivative is undefined there, not 0, I put 0, that's wrong. Because the first derivative is undefined there, the second derivative will also be undefined there, and we already know it's in the domain, so it's a PIV. Does it end up being an actual inflection value? Does the curvature actually change there? Yeah. Second derivative changes from what to what? Negative to positive. Good. So I'm not going to write out all those sentences, but that's how you would do a piecewise function. You actually kind of want to sketch the graph. And then once you have the graph, you can kind of answer the calculus questions based upon what you know about the graph. So piecewise functions, always the fun ones, always kind of the exception to all the rules. So that's all I'm saying about those last two. Okay, so let's talk about the second derivative test again. Like before lunch, the second derivative test is going to be a second way to test for relative extrema. Okay, so here's what it says. Let f be a function such that x equals c is a critical value. So assuming we've already found our critical values, and remember that's where the first derivative at that value is 0 or undefined, as long as the function is defined there, right? So we already have that x value in hand. Instead of setting up a number line chart and looking what the sign of f prime is to the left and right and looking for a change in that sign, we can use the concavity of a function at that point, okay? assuming the second derivative exists. So it would have to be, the function would have to be continuous there, okay? Here's what it says. If the second derivative value at the critical value, you plug your critical value into the second derivative. If it ends up being greater than 0, then what do we know about the concavity there? It's concave what? Up. Well, come back over here to that little diagram, concave up. If you know it's a critical value, you know it's a horizontal tangent line. And guess what? That would have to be down here at the bottom of his smile. It has to be a local minimum, okay? If at a critical value where the derivative is 0, the second derivative has to exist, so the first derivative has to exist as well. So it only works for these types of critical values, not the D and E ones, okay? Because you need the second derivative value there. If the second derivative at a horizontal tangent, that's another way to say it, is a positive number, then it's got to be a local minimum there. And similarly, if the second derivative is negative at a critical value or a horizontal tangent, a specific type, then it's got to be at the top of the frown, which means it's going to be a local maximum. So that's one calculation. Instead of setting up a number line chart and looking on either side, that's a single calculation at a single point and using the sign of that number to determine it. There is a drawback, though. The first drawback is, number one, you need the second derivative. How easy or quick is it to always find a useful version of the second derivative? Just for the purpose of plugging into it. Not always easy, right? Because sometimes it takes a little bit of elbow grease. But for some, if the second derivative is easily found, it's not that big of a deal. That's one drawback. You actually need the second derivative. The second drawback is it doesn't always work. If you plug in and get 0, okay? He's got saucers for eyes. If you plug in and get 0, the test does not work. And that's when you start panicking, like when you're left home alone, okay? The test does not work. And what does that mean? If the test doesn't work, is there another way then to determine if it's a local max or min? Yes, you got to go back and do the first derivative test. Okay, so there's the second derivative test. It's a test for local extrema. Get your critical value from the first derivative. If it's a 0, if it's a horizontal tangent, plug it into your second derivative. If the value there is positive, it's concave up, and it's a local min. If the second derivative at the critical value is negative, it's concave down, it's a local max. But if the second derivative at the critical value is 0, the test is inconclusive. Doesn't mean it's not. It just means the test does not work. And then you got to go back and do the number line test on either side with the first derivative. Okay, let's try it out. Example 5. Find the relative extrema for this using the first derivative test. Okay, so we're kind of back to the previous section. What's the domain of f? All real numbers. It's a polynomial. So here's f prime. It's going to be negative 15x to the fourth plus 15x squared. That's never undefined, so I just need to see where it's equal to 0. So I'll factor out a negative 15x squared, and that gives me a positive x squared minus 1. All right, so if you want to factor that some more, not that you need to, it is a difference of squares. So there it is, and notice that's the full-fledged factored version. So don't divide through by negative 15, because we're going to come back to that. You know then that the critical values are going to be x equals 0, 1, and negative 1. Now let's say this is a multiple choice question, and the question just asked, how many relative extrema does the function have? Relative extrema, remember, is a plural term for both max and or mins, right? So how many local extrema does this function have? It has 3 critical values, but how many local extrema? Are all 3 of those going to be sign changes? No. Okay, remember that the x is squared. That's an even exponent. So although 0 is a critical value, you're not going to see a sign change in the first derivative there. Whereas the other 2 are linear, they're to the first, you will. Now, without doing the number line chart, it's not easy or quick to see if those are local max or mins. But you do know that you are going to have either a local max or min at 1 and either a local max or min at negative 1. So this function has 2 relative or local extrema. That's a real quick way to answer it. But if you had to justify it, you need to know how the sign changes. So let's go ahead and set up our number line chart. X and f prime. We got -1, 0, and 1. There are no discontinuities to worry about. So we'll just pick some test values, 1/2 and 2. Now we don't even have to plug it into x squared because it's always positive. So it's going to be the value of either x minus 1, x plus 1, or you can almost plug it into x squared minus 1 faster and then change the sign. So if you plug in a -2, I get a negative times a negative is positive, and a positive times a negative is a negative. If I plug in a 1/2, I get a negative times a positive, which is negative times a negative is positive. I'm plugging into the bottom one. If you plug in a 1/2, you get a negative times a positive, which is negative. A negative times a negative is a positive. And if you plug in a 2, you get a positive times negative is negative. All right, so notice what happened immediately to the left and right of 0. The sign didn't change. We happen to know now that it's positive on both sides. So at -1, we knew there was a local max or local min. Now we know it's a local what? Min, because the derivative is going from negative to positive there. And at 1, it's a local max. So I'm not going to write it out, but you would say f then has a local minimum at x equals -1, since f prime changes from negative to positive at x equals -1. Make sure you're saying that twice. F has a local max at x equals 1, since f prime changes from positive to negative at x equals 1. And if it did say to address all the critical values, f has neither a local max nor a local min at x equals 0, since f prime is positive on either side of x equals 0. Boom, done. Now, if you were going to list where the graph of f was concave up, could you just go straight from -1 to 1? I'm sorry, increasing. I'm thinking of the second derivative now. Could you say that f is monotonic increasing from -1 to 1? Could you go through 0? Yeah, because it's a singularity and the derivative there does exist. It's just 0. Okay, so that would be fine. All right, so that would be the first derivative test. Now for the second derivative test, if possible. Well, I don't have the second derivative yet. Which version of the first derivative would be the easiest one to use if I wanted to take another derivative? Would it be this full-fledged factored version? No, that would be a triple product rule. The expanded polynomial version is probably the easiest one to use. And it should come pretty quickly. So f double prime now is -60x cubed plus 30x. You can even factor out a 15 first if you wanted. But that's not too bad. And now I set that equal to 0 because it's never undefined. I'll factor out a -30x, and that leaves me a 2x squared minus 1. Oh, wait, we're trying to find what? Sometimes I lose sight of what I'm doing. What am I doing here? I just want to use the second derivative test. Is that the same thing as testing for concavity? No. I'm finding PIVs so I could set up a second derivative chart. That's not what I want to do. That's testing for intervals of concavity. So what I want to do is just take my second derivative, which I can still say is -60x cubed plus 30x, and I want to plug in my critical values. So whether you think the expanded or factored version is easier, I'll let you be the judge of that. But we have 3 of them, -1, 0, and 1. Those are my CVs. So we're taking the values we found from the first derivative, and we're plugging them into the second derivative. So here we go, f double prime of -1. I'll just keep the expanded version. That's going to be a positive 60 minus 30, which is 30. Now, the important thing here is to say that 30 is greater than 0. Now, here's what I would recommend. If you get greater than 0, just to the right, just draw positive signs. Realize he's smiling, and then go ahead and just button his lip if you want. And now you have a visual that it's actually a what? A local min. And so all you'd have to say is, so f has a local min at x equals -1. The justification is a little bit shorter. You don't have to say anything about concavity. Nothing. If you wanted to say f is concave up there, that's fine. What we're looking for the justification is the second derivative, bless you, at the critical value is a positive number. Okay? Therefore, f has a local minimum at that x value. Let's try the next one. F double prime is 0. If you plug it in, you get 0 plus 0, which is 0. What does that mean? Inconclusive, right? All right, so we can't tell. If it equals 0, then that means that it's also a what? Not just a critical value, but it's also a what? It's a CV and a PIV, yeah. Because it makes the second root of 0. And then the second derivative at positive 1, when you plug it in, you get negative 60 plus 30. That makes it negative 30, which means it's less than 0. So when it's less than 0, off to the side, draw negatives. That means you're frowning. And then button his lip, and you can get a visual that it's a max. So F has a local max at x equals 1. Again, that's all you need for the justification. You don't have to talk about a sign change in anything. It's just the second derivative at that critical value is less than 0, and then your summative statement. Okay? And now, here's where you'd want to be careful. If you did the second derivative test first, and you go back and test 0, what could happen if you're only testing on either side of 0, and you put this as 0? What could happen if you're not careful? Choose a number less than 0, like negative 1. You plug it in, and you're going to get 0. You're like, oh, that didn't work. What if I chose negative 2 and 2 then? Would that work? No, you got to be careful, because remember, we already had critical values at negative 1 and 1. So if you are going to have to come back and test one value, go ahead and make the full number line chart with the x values, but you don't have to evaluate this right here and this right here. That'll keep you from picking a value too far to the left and too far to the right. Because if you go past another critical value in your interval or past another discontinuity, you're in a different country, right? You're speaking French in Canada, and that makes no sense. Or maybe it does. Okay. All right, sweet. So what is the second derivative a test for? Relative extrema. Good. Relative extrema. There's two ways to do it. Second derivative test, first derivative test. Now, as we move forward, the second derivative test is actually going to be sometimes the only way we can do it. And why? Here's why. The second derivative test uses information about the function at that same exact point. Is it concave up or concave down? Whereas the first derivative test requires you to be able to find or produce values to the left and to the right of that value. Values that you know are not going to be outside of another critical value or discontinuity. Are we always able to generate our own values? Well, if we have an equation, sure, just plug it in. If you have a graph, you can kind of look to see if the values are positive or negative. But when are we at the mercy of not being able to produce our own values? When you're given a chart. Very good. If you're given a table of values or a chart, that's all you got. You have to use what you have. And so that's primarily when the second derivative test is going to earn its keep, because you'll be given probably information about the second derivative at that point. So let's see if we can get through this example 6. Selected values of a twice differentiable function. That just means the second derivative exists. So the function's continuous and differentiable everywhere. The first derivative is differentiable, so the first derivative is also continuous. And the second derivative exists. So we know we have all those values. It's continuous. It's continuous from negative 3 to 5, and here are the selected values. So we have 3 different x values given, negative 3, 2, and 5, and we have the function value, the slope value, and the concavity value. Okay, cool. Is it safe to say that f is concave up on the entire open interval from negative 3 to 5? Well, a function is going to be concave up on an interval if the second derivative is positive on the entire interval. Agreed? Look at the 3 values that we were given. It's concave up at negative 3, it's concave up at 4, and it has 0 concavity at 5. Well, we're only interested in the open interval. So if it has 0 concavity at 5, that's okay. Just because I have a positive number given somewhere between negative 3 and 5, does that mean for a continuous function the second derivative has to be positive everywhere else? No. How many values are there between -3 and 5 through a continuum? Infinitely many. Infinitely many. And we only have one representative value out of infinity. That's a pretty poor sample size, right? So just because one person is positive, does that mean everybody else in the whole world is also positive? No. Especially if they haven't been through Rachel's challenge yet, right? So, no, we can't assume that. So the answer would be, I'm sorry to get emphatic here, but I'd say heck no. Silly, right? Assuming that they were trying to be silly and not like a serious question, because you would hope no one would really ask you that. That is a silly question. Heck no, comma, because what? We only know that f double prime of 2 is greater than 0 and know nothing about f prime of x for all other values on the open interval from 3 to 5. Something to that effect. -3 to 5, sorry. Something to that effect, right? There are infinitely many more values out there, and we have no idea what the second derivative is there. It could be negative, and that would not be then concave up, right? Any questions on that? Maybe don't say silly, and maybe heck is too strong of a word. I don't know, right? Maybe the exclamation point is inviting anger as well. So how about no? Maybe not even capitalized. How about lowercase? Is that better? That's softer. No, with a comma. No. You don't have to get all uptight. No. Okay. All right. How about the next one? Review. Explain why there must be a z between -3 and 5 such that f of z is equal to 6. Okay. Explain why there must be. That means prove that there exists a z between -3 and 5 such that the y value at that x value of z is 6. What theorem do we use to prove y values? Yeah, the YVT is the IVT. Good. So let's review the IVT. It says if f is continuous on the closed interval. They're telling you that the value exists on the open interval. That's fine. You have to say, what's the function's name? F? Okay, so since, or let's not say since yet. We don't have any data. How about just say f of x is continuous on the closed interval from -3 to 5. You need to say that. Okay? And now we need to determine what is f of -3 and what is f of +5. We need to compute those. Those are the y values at the endpoints. Those are given here to be 0 and 7, respectively. 0 and 7. So what the IVT says is, as I go from left to right, from -3 to 5, I am guaranteed to pass through all the y values between 0 and 7. And moreover, there is an x value on that interval that'll produce it. Okay? Well, the value that we're trying to prove is 6. Is 6 between 0 and 7? Yeah, that's all you have to say. 6 is between 0 and 7. But you say it mathematically. So now you could say since 0 is less than 6 is less than 7. Okay? Comma, by the IVT. And then remember from there, we just reuse their words. There must be a z, blah, 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 blah. Just reuse their words. That's the easiest way to do it. Don't try and like, whoa. I'm really no good at pasting text. Let's try that again. That's as small as I can make it. So we'll just put it right there. Okay. By the IVT, there must be a z in the open interval from -3 to 5 such that f of z is equal to 6. All right. Any questions on that? Now, again, notice it has to occur on the open interval because at -3 and at 5, the value is 0 and 7, which is not 6. But remember, the IVT does make the allowance that it could happen at an endpoint. What about the next one? Review. Explain why there must be a w on the same interval such that f prime of w is +7/8. Now we're trying to prove a derivative. A derivative is also known as a slope. A slope in algebra we use the letter m for. So when you're trying to prove a slope exists, what theorem is it? MVT. Slope VT is MVT. So for this one, you'd have to say f is continuous on the closed interval, -3 to 5. And what else? Differentiable on the open interval from -3 to 5. All right, and now you know then that f prime of x has to equal f of 5 minus f of -3 all over 5 minus -3. The derivative has to equal the average rate of change. Well, set it up like that with your difference quotient, and now just evaluate it. F of 5 again was 7. So we get 7 minus 0 all over 8. That equals 7/8. If you did it right, that should be the value of the slope they're asking you to prove, because that's the only way it's conclusive. Your average rate of change should equal that slope derivative they're telling you to prove to exist. And so now all you have to say is, so by the MVT, and then you reuse their words, there must be a W such that blah, blah, blah equals that. Okay? There must be, I had it highlighted so it didn't take it. Anyway, you get the idea. Okay? All right, and then we're going to have to finish this one up tomorrow. Do we want a quiz tomorrow? I'd rather, you want a quiz tomorrow? Let's not quiz tomorrow. No quiz tomorrow. I want to get through with this section. Maybe we'll quiz on Thursday. Yeah, there we go. Okay, remember to do the worksheet. Yeah, don't forget about the worksheet, Corpy's World. Enjoy the rest of your National Electric